Hello, I'm José Manuel Linares Felipe, and this presentation is a preview of my work during the 2013 Pioneers into Practice International Placement at the Innovation Birmingham campus. On my arrival, we agreed that my placement activity should be the energy efficiency audit for the Innovation Birmingham headquarters building, the Faraday Wharf. The activity will then become a case study I could use for self-training in the tasks I don't usually carry out within audit work teams. So the placement period was dedicated to this. A complete building inspection, data room activity, studying materials and machinery characteristics, and even the original building design philosophy. Users interviews, data processing of blueprints and installations, and of course a first attempt of computer modeling with the design builder software. The final report was also drawn up with a description and photo report of the building, and an exhaustive catalog of construction and installation elements. This work allows us to offer a first professional diagnosis about the building's energy functioning. So, we'll make a quick checkup of every energy usage inside the building, with a first analysis and improvement considerations, and a final proposal based on light retrofit interventions. There is not much to report about electrical lighting. The building is provided with a well-designed system with some energy-saving devices, such as presence sensors. The obvious intervention will be the gradual replacement of the luminaires with LED systems to reduce electrical consumption. Domestic hot water is provided by electric instant generation and storage devices located in toilets and restoration spaces, which is a suitable system for this kind of building. My only concern is the supply of high temperature water that leads to unnecessary electric and cold water consumptions. The existing heating system is based on natural gas boilers. The radiators are mainly located on perimeter walls, maximizing flexibility of internal partitions. As a result, heat is mainly distributed by thermal air convection rather than direct radiation. The same system is used to heat internal spaces and the atrium. Two air handling units partially preheat the incoming air from the ventilation system. Unfortunately, the existing situation is not good. A total juxtaposition of a huge, poorly insulated dispersant surface with a high temperature emission system is the reason for massive thermal losses. In fact, many low comfort areas can be located across the building. On the other hand, several unused hot air sources can also be found inside the building. The first action to take on the building should be insulation. No other intervention will have an effective response before this. A new low-temperature emission system, such as radiant baseboard, could improve the heat distribution across the building without compromising internal flexibility. However, with such a system, appropriate insulation of internal partitions will be necessary to provide thermal inertia to the building. The chosen cooling system consists of a long series of electric heat pumps, each one covering a single workspace or server room. Though this may not be the most efficient design, the functioning of the building with multiple tenants makes it suitable for this particular case. In any case, server rooms are still the main cooling consumption spots. This cooling system is not enough against summer solar radiation. The high glazing and low insulation of southern walls and roof are the reason for a large discomfort zone in proximity to these structures. This situation is being countered with users' manual ventilation with unsatisfactory results. Server rooms are exclusively cooled by energy-consuming systems. Meanwhile, some free cool air sources remain unused. The improvement of the building's functioning in summer should be based on solar radiation mitigation and a well-designed ventilation scheme. Facade shading could be implemented in the respect of the existing building design, while the best roof insulation will be a green roof solution. A real continuous passive ventilation regime could be reached via new Venturi effect shafts. And cooling consumption in server rooms could be easily reduced by free cooling systems. However, the main issue regarding the building's efficiency energy is ventilation, as it affects not only air quality but the functioning of both the heating and cooling system in the building. Currently, a mechanical ventilation system is designed for some internal areas in the building. A dirty extracting system closes the loop for these spaces. The main workspaces are only provided with extraction of exhausted air, finally disposed by the passive ventilation shafts in the roof. Ventilation of the atrium is consigned to natural ventilation by manual opening of smoke evacuators. The current ventilation scheme is not a balanced one. A source of primary fresh air is provided only for internal spaces. Some of them are supplied with secondary air. This scheme is not enough for the high pollution and humidity charge of these spaces. Potential health problems have already appeared in the critical point of the showers. The extracting system in main workspaces has no noticeable effect and therefore is usually switched off. Once again, this situation is unsatisfactorily mitigated with manual ventilation by the users, who in fact show the first symptoms of sick building syndrome. So, what to do then? Our main proposal is a reorganization of the whole ventilation system. A light retrofit intervention using as much as possible the existing installation with some new devices. First, a triple primary air source will be designed. One at the roof for winter use, a second in the ground level of canal side for summer use, and a third one for the winter server rooms free cooling. Second, a well-balanced ventilation scheme should be implemented, with air supply in perimeter walls and extraction by central grids. Third, ventilation of northern spaces and atrium should be run by the same installation. Fourth, a new heat recuperation unit should be installed in the roof plant room. Finally, a new passive ventilation system on the roof should be installed to dispose exhausted air. How will it work? In winter, primary air is taken by the roof intake and pumped into the building. At the same time, heated exhausted air is extracted from internal spaces, server rooms and the atrium ceiling. These two flows converge into the heat recuperation unit, where fresh air is preheated. This new, not-so-cold air is supplied to the workspaces, reducing the heating system consumption. Pre-cooled exhausted air is then evacuated by the passive shafts. During summer, not polluted primary air is obtained from the canal side ground floor intake. A new dispersant long metal conduit along the basement ceiling naturally precools this air, which is pumped into the workspaces, thus reducing the cooling system electric consumption. Sorry. Exhausted hot air is extracted and conducted to the roof level, where it is directly disposed via the passive shafts. In conclusion, a retrofit operation on the building should have these three priorities: insulation of dispersed structures and reorganization of the ventilation scheme, in order to reduce winter thermal losses and the consumption of both heating and cooling mechanical systems. Other interventions are still possible with different levels of cost efficiency, but they should be checked out individually and with more detail. Hopefully, this will be just the beginning of a more exhaustive report on the energy efficiency of the building, with a proper software modeling that will provide data of each retrofit operation. In the meanwhile, I hope my work has brought some interesting points to think about the building, and thanks for your attention. Goodbye.